And hello. So now welcome to this video. So now we are ready to code our function for the Ping-Robinson equation. At least, well, we went through a lot of trouble to understand a lot about Rust structures and so on, just to be able to solve the Ping-Robinson equation. Now, what we are specifically solving for is this equation in particular, which solves for the compressibility factor z. And for this, we are only interested in finding the cubic roots. Okay, we are interested in finding cubic roots. So for cubic roots, we have three real coefficients: b, c, and d. Okay, we have three real coefficients: b, c, and d. Okay, uh, these will be these are necessarily real, and there are two scenarios that we can have. First is that we have one real root, okay, one real root, and the second is that we have what do you call that? We have three real roots, okay, three real roots. Now, if we have three real roots, that means there are two possible values of volume that we can have, or two possible compressible factors. So we usually have a liquid-like root and a vapor-like root. If we have one real root, then I guess we should be in a supercritical phase, or in other words, we only have one real root, and that is the real root of the gas volume. And this is just to recap what we have, why we went through all this trouble to code a cubic equation. It is to find volume given a pressure and temperature. Okay, pressure and temperature. So that's our find cubic roots. So for this case, since we have one real root or three real roots, using a vector to represent this is totally fine. Okay, using a vector to represent this is totally fine. We can of course put this inside a result enum. Okay, a result enum. Okay, we can actually put this inside a result enum, and that can work. Okay, converting this is quite simple, but I the general principle in coding is that if there is no need to introduce complexity, don't introduce complexity. Okay, if there's no need to introduce complexity, don't introduce it. So we'll just leave it as it is. Okay, so I'll have my find cubic roots structured as such. Okay, since there's no possibility of me having so-called purely complex roots, using a vector of float 64, 64-bit floats is totally fine. F64 is totally fine. Now, if we happen to run into problems, then we'll come back. Okay, so now let's go to our let's see whether did I bookmark it. Okay, so this is Harpoon. Pardon me. This is Harpoon, which allows us to hop between files pretty easily. It's a fuzzy finder. It's one of those nice things in Neovin, a great plugin by the Primeagen. So yeah, so it's a great YouTuber I like to watch. Okay, for Neovin related things and Rust as well. So anyway, let's go back here to cubic roots, or not cubic roots, PREOS. PREOS, we are doing the Ping-Robinson equation. So we have the gap pressure. We have the gap pressure code, and that is fine. We have a gap pressure code right here. But we don't really need the gap pressure now. We need to get the molar volume. Okay, we need molar volume. So let's see what we have sort of left off. Okay, we got B. Okay, what is B? B is 0.07780 RTC over PC. So this is the B right here. And if we just Want to see what get B is, this is where the function is. So not too much to be, not too much to be doing there. And let me do screen key so that you can, why does spectacle always come up? Screen key, I want screen key. Screen key, there you go. So I'll just let spectacle come out, screen key come out, excuse me, so that you can see what buttons I'm pressing. So yes, we calculated B. Okay, B is 0.07780 RTC over PC, critical temperature and pressure. We have kappa. Kappa is based on the eccentricity factor, and it is coded as such, so that should be correct. We have R, which is the molar gas constant, 8.314 joules per Kelvin per mole, or joule per Kelvin mole, however you want to call it. Okay, we calculate B, so B is BP over RT. That's over here. A is over here. I just call it capital A. Okay, A times P over R squared T squared. Okay, so A is this, and for some reason I'm calculating kappa and the reduced temperature. That's important for the alpha. Okay, here's the important for the alpha. So capital A is this ratio, and it depends on A, P, R squared, and T squared. This A here, this small a is based on alpha, is based on the kappa, so on and so forth. So I have this expression for capital A already done, so I'm not going to go through again. Okay, so next thing is this, right? Next thing is this. The z cubed 1 minus b z squared plus a minus 3b cubed minus 2b. All of this is already programmed in. Okay, ab minus b squared minus b cubed. So ab minus b squared minus capital B cubed. Okay, so all these have already been done, and what I want to do is solve cubic roots. Solve cubic roots. Solve for the cubic roots. So I'm going to try to bring my find cubic roots equation right here. I'm going to do such. Okay, cat cubic root b equals to, I need to make sure this is a F64 type, and I will just take this is the first one minus, what is that means there? There should not be a means, it's called minus. Okay, sorry, I need to rename this. 1 minus capital B. Okay, so this cubic root b is here, and it will be minus 1 minus b. So minus 1 minus, okay, what is the, 1 minus, okay, never mind, fd yank jd paste. Okay, I'll just get the value out here. There you go. The cubic root b is this value, minus 1 minus b. And let's cubic root c float 64 equals to capital A. Okay, I think it's taking some time. The language server protocol is taking some time, so it's lagging. It's not really initialized yet, and I need to get the value. Okay, now the last one is cubic root d. Okay, actually using value for this, it's it works. Okay, it gets the value of the ratio, but I think the more proper way is to do this. Use the get ratio method so that you are very explicit about what what unit you are getting it, because you're converting from this ratio type, which is a quantity. You need to get an F64 from it. So it's usually good practice to get it with an appropriate unit. In this case, we use the ratio, but ratios can have units of parts per million, percentage, so on and so forth. So we want to be very specific. So making things specific makes things less error prone. It may be a bit slow now, a bit slower to program, but it makes things less error prone and much easier to debug. Okay, so the last one is cap AB. I'll yank this, go here, paste it, and then I'll do the get ratio method. Okay, looks like my LSP is finally working. Okay, after this I can find my roots. Okay, let roots z root values. Okay, f60 this should be a vector of f64. Okay, equals to find cubic roots. Okay, I will get cubic root b, cubic root c, cubic root d. Okay, and it's giving me a problem because I did not import anything in. So it says find cubic roots is not found, consider importing. So use create cubic roots, find cubic roots. So it's very straightforward import. So I just use the code actions, which is the quick fix equivalent in VS Code. I can import the cubic roots, no problem. So I have a z root values now. It's a vector of float64 values, no problem. So next thing I want to do is to arrange these values. Okay, and of course now the code's going to be messy, but doesn't matter. It's okay. Okay, we can tidy things up later. But for now, let's just put a comment here, say find roots. Okay, find roots. Okay, cubic root. Oops, this should be B. Yes, good thing there are lints and warnings to tell us what's going on and what's good, what is not good. So all that's fine. Z-root values, these are vectors of x64. We know that there are two cases. There's a case that we have numbers, and the other case is that no, there are three roots, and then there's a case that there's a one root. So these are the two cases we need to handle. Okay, so these are the two cases we need to handle. Of course, having a vector of f64, it doesn't tell us anything about what the root can be like. Okay, it doesn't tell us anything about how many roots there are in this case. And then we have to use manual if statements. Of course, the more so-called compile time safe way to do it is to use the an enum for 3 real roots and an enum for 1 real root, but doesn't matter. You don't need to overcomplicate things at this point in time. Okay, so I want to convert this vector of f64 into a ratio. Okay, I want to convert it into a vector of ratios. So let's z and then of course I want to order it. Yeah, order the z roots first. Okay, if there are 3 real roots. Okay, so there are two cases. Yeah, two cases. Okay, so let's do case 1, 1 real root. Okay, case 1 is that one real root. Okay, so there are two cases. If z root values, okay, what is that? Z root values dot length equals to 1. Execute this line of code. Okay, z Okay, there you go. Zroot values dot length equals to 1. Okay, execute some of this. Then case 2 is 3 real roots. Okay, then order the z roots first. Okay, so let me do the if block. Z root. Okay, values dot length equals to 3. Execute this. Okay, otherwise there's gonna be a problem. Okay, I'm gonna say there is some sort of error here. Panic error. Okay. What's the error? I don't know. Unable to find volume roots. Okay, so let's just observe what the molar volumes are. Okay, so this is the get molar volume Ping Robinson gas. So this is going to be sort of, well, it's just going to return one value. Okay, it's going to return one molar volume value, but for Ping Robinson equation of state, there can be a case where there's more than one volumetric root. So we have to take that into account as well. That is something we will do later. Let's deal with a simpler case first, where there's one real root. So good practice is to just tackle the easier problem first. So okay, if the root value is 1, okay, the z root value is 1, okay, let z value equals to z root values dot first. Okay, there's something wrong here. C2. Okay. C. Okay, so it's the first. Okay, this is going to be a z value. Then let's unwrap it. Okay, of course, again, this is not the best practice, but let's just get this code out and running, and then we'll deal with this result stuff later. Okay, so this is the NF64, and let's do a to owned. Okay. Or maybe I'll do a F64 here. Then I'll use a dereference operator. Okay, so let me see to the semicolon. Okay, it says a mismatch of types. Okay, so I'm just going to do a dereference operator. Okay, again, we are dealing with references and pointers, but at this point in time, or references. So at this point in time, just let the compiler guide us on what to do. Where do we add the asterisk? Where do we add the ampersand sign? Don't really need to know too much about references just yet. Okay, we have to come back to that later. So if the z root values equals to 1, all right, if the z root value equals to 1, then we can quickly find our z value, our only z value, and then we can actually find what are we looking for? We are looking for the volume. So we need ZRT over P. Okay, so ZRT over P. So let's, okay, I'm going to do a allow snake case here. Allow a non-snake case. Let's z equals to ratio new value z value. Okay. And this should be a ratio. So this is going to be the z value we have here. So to get our molar volume V tilde, okay, the V tilde, okay, let's see, molar volume. Let V tilde, okay, and this must be molar volume. Okay, this, oh, okay. Why isn't the autocomplete working? Never mind. the molar volume is as such. Okay, let V tilde molar volume equals to Z times, where's your R? Where is R? Molar gas constant. R is the molar gas constant. Molar gas constant times temperature divided by pressure. Let's see whether this works. Okay, things seem to work. Okay, so this is the correct quantity, and then I'm just going to return V tilde. Okay, so right, this one's pretty straightforward. I get the value of Z. I multiply RT to the other side and I divide by the pressure. The nice thing about the units is that it allows me to check for the correct units at compile time. So I don't need to worry about units once this thing compiles, right? So this is the one railroad case. Now let's consider the fact that we have we have three railroads. Okay, we have three railroads. Okay, so if we have three railroads, we first want to order them in three railroads first. Okay, we want to order them in three railroads. Okay, so how do we order them? Well, we can just simply go to, let's see, file buffer. Let's see, file buffer. Yeah, three railroads. How do we order them? Okay, order. Let's see. So the simplest way to order, as we can see here, we use this sort by partial CMP. Okay, and then we use the maximum and minimum root to get them. So I'm just going to copy this over and paste since we already did this before, and I'm going to change this solution vector to Z root values dot clone, and then I will get the max root and min root be as such. Okay, these are float, if I'm not wrong, float 64 values. Okay, the max root is the max Z value. Max root of Z is the maximum compressibility factor. Okay, so all else equals, if Z is large, then V is large. So a maximum compressibility factor, so to speak, Z, this corresponds to vapor-like roots. Okay, the other one is liquid-like roots. Okay, liquid-like roots. Okay, so how do we sort of get this molar volume for the Ping-Robinson gas equation? Okay, so there are two ways. I mean, this code can actually do two things. First thing is that, yeah, let's just return the vapor-like roots only. We don't want to bother with the liquid-like roots. The second thing is that, well, if there are vapor-like roots, okay, if there are vapor-like roots and liquid-like roots, then we return them in a vector. Okay, may or may not be the best way of doing things, but that's certainly one way of doing things. So the simplest way, in my opinion, the simplest way is that I will just code the function to get vapor-like roots. So I'm going to have, I'll do this here. I'll make it very explicit. Vapor-like roots. Okay. So for this, I will only return vapor-like roots. I do not want to return liquid-like roots so that I don't have this so-called vector problem. Okay. So this minimum root, this liquid-like roots, I'm not going to even bother with this. And I'm just going to return the maximum roots right here. And as usual, I'll do this. I'll just copy this bit of code here. Okay. Now, generally, you don't want to repeat lines of code. This is what we call boilerplate. Boilerplate is basically unnecessary lines of code that are repeated. But if it makes the code easier to read, then sure, why not? Okay. and this should be called molar volume. Okay. Yeah, probably did the undo by accident. So I have a v tilde here. Yeah, okay. Okay, let me try that again. I think I made an error. So let's do this here. MB CRW max root. There you go. Now we have unable to find vapor light volume roots if there is an error. Now, no matter what our values of P and T are, we should be able to get at least one root. Okay. Now, apparently, my kappa is not being used right here for some reason. Yeah, my kappa is not being used. Okay, why? Because kappa is already being defined here. So, well, apparently I can just delete this piece of code and that should give the right value. Okay, so this function gets us the vapor light roots, okay, from the Ping-Robinson gas equation. Okay, vapor light and let's see. Gas and vapor light roots. So this is some this is very weird way to name a function. PREOS gas and vapor light roots. Okay, maybe that's a better naming convention. Okay, so I have this thing. The second thing, of course, I need to do is to get the liquid light roots, just to make it more complete. So the liquid light roots, pretty much I can copy most of the code here. Okay, let's go to gas and vapor. Okay, I'll use liquid light roots here. Okay, so for liquid light roots, the thing is that we don't always have liquid light roots. Okay, liquid light roots assume that there are at least two roots. Okay, we assume there are two roots. This function assumes that we have two roots, so there are two possibilities, right? There's a case where we have one root, and there's a case where we have two roots. If we only have one root, then this function is not really going to give you a valid value, correct? So in that case, for this case, using the result enum is very useful because we know we cannot always have we cannot always have a liquid light root. Okay, it's either a vapor light root or gas root. So this one we have to assume that there are at least two roots there. So we can return a result enum. Okay, for now I'm going to use the string error type, but I'm going to tbd change error type to a proper error. Okay, so it's to be done. That's something we need to do later. Okay, so most of the internal logic of the code is the same. Okay. Okay, so for the case of one real root, we have to return an error. Panic. For now, I'll just use the panic keyword. Okay, panic macro to kind of make sure this is not working. Okay, the proper way is to return an error, but I want to deal with that later. The string error type is just a placeholder. Okay, so the only thing here is that when we have three real roots, for three real roots, we are only interested in the minimum root. So this is the liquid light root here, and I'll comment out the maximum root. So FW here, min root. Okay, so now my LSP at least is working. Okay, so now this should work, and what I want to return is the v tilde in the OK variant. Okay, so this should be quite okay. Okay, so the error message should be unable to find liquid light volume roots. Okay, so well, we spend lots of time getting the results. It's for cases like these where we cannot get liquid light roots. If we cannot get liquid light roots, then we sort of return a result. We return results. Okay, we return a result enum, and we explicitly say that there is going to be an error. Okay, so this is the thought process behind the code, and this is why result enums are good. Now, of course, we need to actually have a proper error type because we don't have a proper error type as mentioned before. So let's go and find the error type. I'm going to use the same template as this dot product error. Okay. Okay, I'm going to go B sharp. Yes. I'm going to put the error type here. Yeah. I'm going to put dot product error. This one's going to be called ping cubic EOS error. Okay, I'm going to call this the cubic EOS error, and I want to use this error. Oops, my LSP was very slow, but this is what I can do. Use this error, and I'm going to do the cubic EOS error. Okay, first thing first, what are the errors? Okay, no liquid light roots. So that's going to be one of the errors. Okay, and of course I can add the errors as I go along. So no liquid light roots, that is the error. That's the error description. So I'm not going to do anything. I'm just going to make this cubic EOS error. I'm going to derive it like such, and use this pound sign error. We call this an attribute. Okay, I just had to look that up online. I don't have everything off my fingertips, but this is what I do have. So yeah, we will put this cubic EOS error within here. Cubic EOS error. Okay, and this should be able to compile. And what I want to do is over here, return error. Okay, cubic EOS error. What is this error type? This error type should be no liquid light roots. That's the error type. Okay. Where's the enum? Yes, there you go. No liquid light roots. So the LSP does take some time. So having the no liquid light roots, that is what our error will be. It's very precise. It uses the enums. It derives from the Rust error type. So that is how we should code our Ping-Robinson equation of state. Okay, so these are the functions that helps us to get the volume of the liquid light and the vapor light roots for the Ping-Robinson equation of state. Of course, we will now have to test it. We should have to test the equations of state. So that and more probably have to do it in the upcoming videos. So I'll stop for now. I'll see you next time. Okay, bye bye.